Hey guys,
Hey.
sorry about that. I was reading and lost track of time. How's everybody doing?
Good. How about you?
Doing all right. Um, Getting by, staring down the barrel of the last week of classes.
Did you receive my homework?
I did. Didn't I respond to you?
Yeah, but I sent another file that same
Yeah, I
day.
saw. I saw that one also. Yep.
Okay, thank you very much. I'm sorry for that.
No, not a problem. All right. I just have a couple of things to go over with you today. Both of which are going to help you not only with dealing with analysis of covariance, but also will help you with the linear regression problem, the linear regression write-up that you're doing with the Gecko data. So let me share my screen with you really quickly here. So can you guys see the screen?
Yeah.
Okay, so this is back in the regression example that we had with the relative humidity and the mass loss of the beetles. And what I want to do is I want to just add one thing to this script for you. That will help you. So we tested the model here, which the model is basically how is weight loss being affected by relative humidity. And just to make sure you guys are doing this correctly, always put the response variable first in your R syntax. So it's a simple thing and sometimes it gets messed up. Whenever you're running a regression, you start off with linear model and then the dependent variable is always in front of the tilde and the independent variable is after the tilde. And so whatever your response variable is, whatever the variable is that you're interested in, how it's responding to something else is always first. So when we run the model and get the summary of the model, these are the outputs. And so once again, we had this very small slope, even though it was significant. Well, in the data for the Gecko project, one of the questions that the researcher has is the relationship between wall temperature and body temperature that relationship is a positive slope, but for this species to be a thermoconformer, the slope of this relationship is equal to 1. So the standard linear regression is always testing against a default slope of 0. And so when you run this and it tells you that relative humidity is a significant predictor of mass loss in these beetles, it's basically asking, does the slope of this line differ from a slope of 0? Well, you can actually test whether or not that slope is different from a slope of 0 or a slope of 1 or a slope of -1. You just need to type in here, this is in the car package. So up here at the top, we loaded car because we knew we were going to be needing certain functions. So this line here that says linear capitalized hypothesis, you put in the model that you're running and then you basically say, I want to test against a particular slope. So in this case, we're going to test against the slope of 0. And when we run that, we see that we get the same p-value and the same F statistic and everything else that we see when we ran. Oh, it doesn't give you an F up here. Oh, there's the F, 267.2. 267.2 is the F. The p-value is the same, 7.82 times 10 to the minus 7th, 7.82 times 10 to the minus 7th. So we can change this to say, well, is this different from a slope of negative 0.05322? And when we run that, we will see that the F value is 0 because we're basically comparing a restricted model that is the same as the slope of the model that we ran. The p-value is 1. There's absolutely no difference between the two of these things. So to test the hypothesis that these geckos are thermoconformers, you want to run tests where you test to see if the slope that you observe is actually different from a hypothesized slope of 1. And this is just a quick and easy way of doing that. And so when you get this output down here, model 1 restricted model is the model that you gave it, the slope that you gave it. And the second model is the model that you ran testing it versus a slope of 0. And if those two things are different from one another, then the slope that you've given it is not as good as the slope of 1. And so you're looking for, if they're similar to one another, you'll look for non-significant result, and if they're different from one another, you'll have a significant difference between these two models. So this is a model comparison kind of test.
Dr. Kowinski?
Yes.
How do we know what number to put into that linear hypothesis code right there?
In this case, the researcher has given it to you, because if a gecko is a thermoconformer, then if the wall temperature is 10 degrees centigrade, then the body temperature of the gecko should be 10 degrees centigrade. If the wall temperature is 20 degrees centigrade, the gecko temperature should be 20. If wall temp is 30, gecko temperature should be 30. So this should be a 1-to-1 line, which would be y equals 1x plus whatever the y-intercept is. So even though the researcher hasn't said, I expect there to be a 1-to-1 relationship, the description leads you to that conclusion. So in this case, it would be a slope of 1. And in almost all cases, researchers typically test either a slope of 1 because we're interested in whether something has a 1-to-1 relationship, or we're interested in a slope of 0. In most cases, we're interested in whether something is different from a slope of 0, which is why the default in R is to test that hypothesis.
So when we do the gecko work, we, instead of negative 0.0532, we'd have a 1.
Yep.
And then down in the results, we'd be looking for a high p-value.
You would be looking for a non-significant result, because a non-significant result would be the regression slope that you observe is not different from a slope of 1, which means that they are thermoconformers.
It's not.
So, and you can see when we test against a slope of 1, it's a really large p-value, because not only is it different from a slope of 0, the actual regression here is negative rather than positive. So yeah, you would just put a 1. Whatever your slope value is that you want to test against, that's the slope value that you put in there.
And a p-value higher than 0.05 tells you it's
not different.
Right. Okay.
Not different from that slope value. So we could also test to see if that 0.05 was different from a slope of -1. And it's also different from the slope of -1. It's a really shallow slope, but it's significantly different from 0.
Yeah.
So in this case, let's just do this. Oh, crud, I messed up. That's not what I wanted to do. So this would be a slope of 0. And so that's clearly different than a slope of this line is clearly different than a slope of 0. But you could also plot, you could, instead of making this horizontal line due to the y-intercept of to the L mean, we could also what is the y-intercept? It's from a summary model. Let's see. We could also just as easily put the regression equation into this and put the y-intercept in here and the relative humidity of having a slope of -1. We could illustrate what that slope would look like. It would be much steeper than this slope here, and we would also see that this line is different from a slope of 0, but it would also be different from a slope of -1. And both of those hypotheses are supported when we test them quantitatively. So whatever your slope is that you want to test against, that's the slope that you put in here. And the reason that I put -0.053222 is because that's the actual slope that was returned by the model. And when you are testing against the exact slope of the model, you find that the model is not different from the hypothesized slope because you forced it to be equal. And so it returns a f of 0 and a p of 1. Those two slopes are not different because that is the slope that is returned by the data. So anyway, so yeah, you would just run this line on your different regressions and you would put in here a slope of 1. Because if geckos take on the same temperature as their environment, then that is the very definition of a thermoconformer. If they're taking on a different body temperature than the temperature of their environment, then they're doing some form of thermoregulation, in which case you would find that your regressions are different from a slope of 1, and then you would need to know what direction that difference was. Is it a slope higher than 1? Is it a slope lower than 1? What exactly is going on there? Okay. Questions? Other questions? All right, then let's go back to the thing that I started talking about last time. So I'm going to go back to the analysis of covariance example. And now I'm going to have to run through a bunch of code to get everything loaded back up since I just cleared things out. It sounds like somebody is jackhammering something in our building. Can you guys hear that?
No.
Oh, okay.
I don't hear anything.
It's vibrating through my core. Okay, so I've already made the point about why analysis of covariance helps you with over analysis of variance. We were going through the tests for all of the different assumptions. One of the tests is normality, which you just test the same way that you've tested normality in all the other ways. You run a Shapiro-Wilk test on it. You hopefully look at some diagnostic graphs that tell you that you're not too far out of whack. There's a test for homogeneity of variances. You can run the Levene's test, same way that you've run the Levene's test before. Once again, we're all good there. Testing whether or not the independent variable and the covariate are independent with one another. In this case, is the covariate IQ, does that vary across groups? And when you do this, it shows you that they are not different. And then the last thing, and this is what I was just getting to, is the homogeneity of variances slopes. So this is basically testing to see if two slopes are different from one another. And it's analogous to the thing that I just showed you, in that you have one regression that has one slope and you want to see if the slope of the other regression is different from that. And so the way I've always read that you do this in R is basically to write your linear model, but in this case, rather than putting a plus between the independent variable and the covariate, which would force it to do an analysis of covariance, you put the covariate in there as if it's another factor. And so you run the interaction on it. And the reason that this makes intuitive sense is that if you have IQ score and memory score, and you have the drug group and you have the placebo group, if those lines are parallel, the drug group is affected in terms of memory score by IQ in the same way that placebo is affected by IQ. And so there's no interaction here. If, on the other hand, the drug group responds differently than the placebo group, this would indicate that IQ is interacting with memory score across these two groups, and that would be due to the changes in these two slopes of response. And so it makes intuitive sense that this is how you would go about doing this. So when you do this for these two groups of data, and let's go back in all of our plots, and I realize there are so many plots now in this R script that you don't know what to do with yourself probably. We do see that the slopes are not parallel before we have forced them into parallelism by doing an analysis of covariance. What we do when we do an analysis of covariance is we calculate what the pooled slope is, and then we make both slopes equal to that pooled slope. And this is what that looks like. But what we want to test is, was that a valid thing to do? Are these new slopes within the confidence intervals of the old slopes, the original slopes, before we force them into a pooled slope? And so what we do is we look at the interaction term here. And the interaction term, the group by IQ interaction term in this case, is not significantly different. And what I've always done is I've just taken this at face and said, okay, the sums of squares for the group by IQ interaction here is 1.397, and there's 1 degree of freedom, and so we would divide the mean square residual into the mean square due to the interaction term, and we would generate an F statistic. We would take that F statistic and test it and find a p-value of 0.53. So then I was sitting around at home a couple of days ago and thought to myself, I've never actually tested to see if that's actually giving me the right answer. And because I do not trust computers, you guys should now know that I have a healthy mistrust of computers. That is not the figure, the PowerPoint that I wanted. I decided to go and see if it's actually giving me the right answer. And so this is what I was going through with you at the very end of class last time. Comparing regression lines, you can calculate what the sums of squares among betas is by basically looking at the x-square values, the individual slopes, and the pooled slope estimate. And the pooled slope estimate is very similar to the slope estimate that you would get for a single line, but this is summed across both lines that you're comparing in this case. And you can see that all of these values, x times y and x squared, these are all values that you initially took from your initial calculations of doing a regression line. So you have what all of these things are. It's just a matter of summing them up. Now, the problem with doing this in an analysis of covariance is that you have these two lines, and it's not so easy to separate these two lines out. And so what I did was I sat at home the other night and put together a bunch of lines of code that does this. So just hang with me for a few minutes. And this is in the most updated version of the ANCOVA example code that I posted. I posted on Wednesday, actually. So if you want, you can also open that up and follow along. So the first thing you have to do is you have to get the two independent groups of data in their own data files. So I'm going to basically take the original data file, and I'm going to make a new data file called placebo. And you can see down here in this data file here, all that's here is placebo. And we still have y hat and y hat line, the linear y hats, because we calculated them for making some graphs earlier. Once we have that data frame built, we need to find out what the average value of x is for placebo, and we'll put that in there. So this is the average IQ for placebo, and then we want to know what the difference is between the observed IQ for each value and the mean IQ score. This is what basically x is in our initial, our old example. No, not that one. La. Oh, let me go back to this is this x, the deviation from the mean of x. That's this column here. And so I'm just maintaining these same notations. So we can also do that for y, and then we can calculate what xy is, and then we can calculate what x squared is. And so I'm just adding x, y, and x squared to the original reduced data file that just has the placebo data. Now I can sum these things up. I can get the sum of x squared, and that's 107.2. And I can get the beta value, which is the sum of x. Oh, I skipped some lines. I can get xy, and then I can get the sum of xy. I can get x squared and the sum of x squared. And from that, I can get the slope value for the placebo. So when we look at this line has a slope of 0.46. That's that line slope. We've done that for the placebo data. Now we can do the same thing for the drug data. First thing we want to do is reduce the data frame to the point that it just has drugs. We want the average of the IQ of the drug group, and that's 118. Then we can get the deviations of that, which is x. We can now find out what the average score of y is. and there, we already did that. We found y hat was 13.8. The deviation of y from that is now in the y category. So now we can get xy, which is there, and we can get the sum of xy. We can get x squared, which is there, and the sum of x squared. And now we can get, oh, I didn't do the slope. Slope is, in this case, we want d beta, we want d sum xy, and d sum x squared. So we can get the slope of this line. And you see that the slope of this line is steeper than the slope of this line. The slope of this line is 0.64. The slope of the other line was 0.46. So now we can calculate the common slope. So quantity 1, the common slope, once again, let's go back and look at this. The common slope is this quantity divided by that quantity. And this quantity is just the sum of all of the xy's across both lines that you're comparing. And so quantity 1 is p sum xy plus d sum xy, p sum xy being the placebo sum of xy, d sum xy being the drug sum of xy. That's 97.18. And then the denominator is the sums of x squared for both placebo and for drug. And so that's quantity 2. And then we can just get the shared slope value of quantity 1 divided by quantity 2. So the shared slope is 0.53, which makes intuitive sense because 5.53 is kind of in the middle between a slope of 0.46 and a slope of 0.64. And so that's the slope value. And when we go back to comparing the lines, we need the slope value of each regression and the pooled slope value that gets squared, and that's multiplied times the sum of the x squared for a given slope. And so you do this for however many lines it is that you are comparing. So now we have to go back to this and get our slope values, make sure that that is the correct slope value, and it was 0.46. We can get the slope value here, and that is 0.64. And so the numbers that we calculated are the numbers that they calculated. So now what we have to do is do a bunch of extraction. And so what we want to know is we want to know what these coefficients are. So I'm basically going to put the coefficients into a new little form here, model coefficients. I get the structure of this, and sometimes when you want to know how to get, so what I want to do is I want to extract things from this model output. And so in order to know how to extract those things, I need to figure out how this is structured in our language. And so what I see is that the coefficients, the y-intercept and the slope value, are in model P, and it's in the column called coefficients. And so if we look for model P $ coefficients position 2 here, it should give us that value, which is the slope value. So this is position 1, this is position 2. So when we do that for the placebo and we do that for the drug, it should return to us just the 2 numbers that are the slopes, those things. So now we have two assigned variables that represent the slope of P and the slope of D, which is the slope of the placebo group and the slope of the drug group. So now we can calculate the sum of squares among, which is the P sum of x squared times the slope of placebo minus the pooled slope estimate squared plus the sums of squares from the drug times the slope of the drug minus the pooled slope squared, and that should give us the sum squares among betas. And what we find when we do that is the sums of squares that we've calculated using the elements of the equation that is shown here, and calculating the pooled slope estimate for ourselves, we get a sums of squares value that is 1.394266. Which should be, why is it different? Which should be the same sums of squares value. Oh, because I wrote it down wrong. Which should be the same sums of values that we got when we ran the R way of comparing for homogeneity of slopes. So we generate the same sums of squares value when we calculate it ourselves, going through quite a lot of trouble to calculate it ourselves, that just running the linear model with the interaction term in place, it gives us the same slope value, 1.394 and 1.394. That convinces me that R is doing this in the correct way. And so we can just not go through all this rigmarole and just test it the way it's been programmed. And so you don't have to do lines 367 through line 455. All you have to do is run the two lines of code that are 364 and 365, running this as an interaction term, test the homogeneity of slopes. If you run that same line of code, well, let's do it this way, but change this to a plus instead of an asterisk, that doesn't test homogeneity of slopes. This is just simply the original model that we tested. And that is the analysis of covariance, where we found no difference among the two groups. Is that right? Is that how it turned out before? No difference between the two groups, but there is a significant difference, a significant effective regression. So if we come down here, wait, why am I getting different answers? Oh, okay, here it is. I was asking for the wrong output from it. So significant difference among groups and significant effect of the IQ. So that's the difference between running a test for homogeneity of parallelism and just running the data as an analysis of covariance. So you've checked all the assumptions. This data set meets all of the assumptions. And so one of the things that you might want to do is to know if you have multiple levels of your independent variable, you might want to know which of those is different. In this case, we only have two. levels, and so it doesn't really matter. It's just telling us drug is different from placebo. But you could use the HH library, which we loaded earlier, and you could run post hoc tests on this. So the first thing that you have to do is you have to run the ANCOVA using that package, and then you can basically take that and you can run a two-piece test on the adjusted values. And so where you can do post hoc tests, and in this case, all it's doing is it's comparing drug and placebo. But if you had multiple levels, it would give you a report that told you not just the difference between placebo and drug, but it would also tell you all of the other kinds of differences that you might see. And so this just tells you, what's the estimated difference between placebo and drug. The estimated difference is -2, and the lower and upper confidence intervals are. And so this is one of the problems with running post hoc tests sometimes, is that when you run a post hoc test, you've used up some of your degrees of freedom, and you see that this is no longer showing this as a significant difference, because you're basically testing the data again to tell you what you already knew, which were that these two levels are different, but you've now used up some of your degrees of freedom, so you don't have as much power. And as a result, the post hoc test doesn't find them to be different, even though the overall ANOVA did. This would be different if you had multiple levels of whatever your treatment group is. So you can do post hoc tests just like you can do post hoc tests in anything, and you do it using, for ANCOVA, you have to use a different package because the regular statistical packages in R do not do it. Okay, so that's that. That should give you everything you need to have in terms of can you guys hear that now?
Yeah, I can hear that one.
Yeah, it's loud in my office now. I'm gonna have to go see what's going on up there. So that should give you all the tools that you need to do an analysis of covariance. So what day is your final? Where's the exam schedule? Oh, exam schedule. So your exam for spring is 7:45. Thursday. So Thursday, by the end of the day, I will need a analysis of covariance report from you guys. And I haven't prepared the assignment for that report yet. I mean, I have it from previous semesters. I just haven't taken the time yet to go back and look at it. Let's see. But I will pull it up now and see what kind of shape it's in. So this is kind of what I got. From a dean a long time ago. This would have been 2003-ish. And I've changed the names here to protect the innocent. So this is a letter to Dr. Ronald Fisher. Ronald Fisher actually turns out to be a biologist who was also a statistician. Lived back in the first half of the 20th century. The F statistic that you calculate when you run an analysis of variance or an analysis of covariance or regression, the F is for Fisher. He's the person who invented the analysis of variance. And so I got a letter kind of similar to this from a dean that we had back in the early 2000s. And it was asking me to look at these data and say, you know, see if there are any issues with faculty salaries having to do with both gender equality and whether or not full professors are having their salaries compressed over time, because we keep giving new faculty higher and higher salaries, but once you reach full professor, there are very few opportunities to get a raise because you've gone through all the steps of going up kind of the academic ladder, so to speak. So he sent this to me and I said, well, unfortunately, I can't really make a determination because you've just given me a bunch of summary statistics. And one of the problems with these salaries is that these salaries are going to be influenced by, among other things, the number of years that somebody has been working here. And so at that time, for example, there were these 2 math professors who were here, but they had only master's degrees. And one of the rules at William Jewell College is that you can't proceed beyond the assistant professor level with only a master's degree. You need to have a PhD in order to be designated an associate professor or be promoted to a full professor. So there were these 2 math professors who had been here for like over 30 years or something like that, who were making quite a lot of money as assistant professors because they had been here for so long. So every time everybody gets a raise simply because of cost of living adjustments, they got one of those, even though they were still stuck at the assistant professor position because they only had master's degrees. So years of service becomes an important predictor of what faculty salary is, and that is independent of rank. Obviously, full professors have been here probably for many years longer than associate or assistant professors as well. And so I really needed more information. And so what I basically said is, I would not present these at the fall faculty workshop and the fall trustees meeting because they're very misleading in the way that you have summarized them, because there's quite a lot of variation in faculty salary. You see how much variation there is at the assistant professor level, especially in the male category, because those 2 professors who were assistant professors who had been here for a really long period of time were adding significantly to variation at the assistant professor level because of length of time that they've been here. So anyway, he sent these to me and I said, I can't do this for you because I actually need more information. And so I wrote him back and told him that and said, I can do a better analysis for you, but I need access to the raw data and I need access to years of service and some other descriptive data in order to control for these other things that might be influencing salary beyond the 2 things that you're interested in, which is, are these differences among ranks indicating compression, and is there gender inequity? And I did that partly, I did that for 2 reasons. One is I actually thought it would get me out of having to do this, because what dean would willingly hand over the salary information of every faculty member at William Jewell College to an untenured biology professor with a reputation for bucking the system? And then no one was more shocked than me when he just gave me the data. He had stripped the data of all identifying information, but he had also given me the information by department, because there are some departments where you get paid more than other departments simply because you could be making more money, for example, out in the business field. And so, wow, that's loud. So anyway, I wanted information on departments because that also is providing some variation in the data. Unfortunately, you couldn't use that in an analysis very easily because some departments didn't have all levels of professors, assistant, associate, full professor. And so I kind of did the best analysis that I could, but the analysis that was appropriate to this was an analysis of covariance. And at the end, I basically ran all the data and found that there was a pretty significant gender gap in pay at William Jewell College, mainly due to historical patterns of hiring. And the difference in pay was about $2,500. And one of the things that came out of that discussion with the trustees and with faculty and the administration is they went about a process of taking steps to equalize pay, such that now when you're hired as a male or a female at Williamsville College, you're basically hired at the same level of pay without any sort of gender discrimination. So it's a very real world kind of application of this idea, using an analysis of covariance to remove unwanted or control for unwanted forms of variation to get a picture of what's really going on. The cool thing about it is that it was also used to facilitate change at an institution where I worked, and that was nice as well. Even though the dean wanted me to show that there wasn't any gender inequality, the data showed that there was, and as a result, we made changes in terms of how we hire people and how we compensate people, which was nice. I was asked to erase all of the data after I was done with the analysis, which I did, but I still had the report. And in the report were figures that showed the regression between years of service and salary and things like that. And so when I started teaching this class many years later, I pulled up that report and basically scanned in the figures and basically estimated what all of the salaries were from the original figures. So the data are going to be slightly off of what the original data were, but they're not very far off. And the data that I'm going to give you are not so far off that it changed the overall conclusion. So I need to go back and look at that data set, make sure that everything in it is correct, and then probably over the weekend I'll post that assignment. And it'll be a similar sort of thing. Your job is to analyze these data for evidence of salary compression and for evidence of gender inequity, and to provide a report to a dean of a small liberal arts college who really knows nothing about statistics, and to do that effectively in a way that will make him understand the data, but also will help him communicate what those data mean to the Board of Trustees, some of whom might understand things about statistics or not, but also to liberal arts college faculty, once again, most of whom do not understand what statistics are about. And so that's always one of the tasks, is making the results of what you've done understandable to people who don't have any clue what you're doing. And that will be your final report, and that will be that. Questions?
I have a question about the upcoming report.
Yeah, sure.
So when I read through it, it seemed like the gecko part of it would be the linear regression.
This is all linear regression.
Yeah. But are we also doing a two-way ANOVA on this?
You're not. Why are you not?
I don't know. It just kind of seemed like we were, because in the last paragraph, we're examining like the difference between two populations and by season.
Okay, so the data can be partitioned in that way, but what the researcher is asking you about at this point is asking you two things. In the temperature part, he's asking you, because he's not very bright. In the temperature part, he's asking you, is wall temperature correlated with body temperature? And he hasn't stated it to you in this way, although it's clear from the description that I've given you that the slope of this line would be equal to 1 if these guys are thermoconformers. Now you can divide these data up. You could treat the entire data set as one big data set. Just throw all of the data from all the populations, from all the seasons into one pile. But one of the problems with doing that is that you're going to have a cluster of data down here that are winter Oklahoma City geckos, another cluster of data right here that are winter Galveston geckos, and two clusters of data up here that are summer Galveston and Oklahoma City geckos. And so it's like you're drawing a line between 2 points, and that's going to actually give you an inflated view of what this correlation is. And so you could throw all of the data in there together, but a better way possibly to do this would be to say, in each population, in each season, what is each regression like? And so you might want to do separate analyses on Oklahoma City, winter, Galveston, winter, Oklahoma City, summer, and Galveston, summer, to see if those regressions are all similar to one. What you might expect is that when it's warmer, there are more opportunities to thermoregulate, such that in one season, you might see that that slope is different from a slope of 1, whereas in another season, you might see that that slope is fairly similar to 1, so that they thermoconform at some times of the year, and maybe they don't thermoconform at other types of the year. So if I was writing this up for this researcher, I would probably run all the data together, and then I would probably divide the data up by subsetting it by using the filtering command in tidyverse, make a set of subsetted data for each population season partition of the data, and then run 4 separate analyses. And in all of these analyses, I would always be testing to see if the slope was different from the slope of 1. Now, the second question is about body size. So this researcher, when he collects his geckos, he always weighs them and measures their length. And so he has a snout vent length to body mass ratio. And what we typically do in herpetology, because once again, herpetologists have just always done this, is they would just divide weight by SVL, get this ratio, and analyze it. But we know that ratios are poorly behaved. And so a better way to do this would be to look at what is the slope of the relationship between Galveston geckos and Oklahoma City geckos. And when you make a plot of it, let me share a plot. And just so you know, these gecko data are my data. So I think a lot about these kinds of issues because I'm insane. So this is when I talk about wall temperature and body temperature, I'm talking about the body temperature of a gecko on a wall and the wall temperature right next to them. So because of that, you might expect these things to be fairly well correlated. Have I shown you guys this PowerPoint before?
No, I don't think so.
No, I haven't seen it.
Pardon?
No.
I
No.
haven't seen it.
Okay, so there's this idea that body temperature is related to performance in geckos, and so at a certain temperature, you reach your physiological optimum. You get much above that, and you start to die. You get much below that, and your physiological, the chemical reactions that drive your physiology just slow down until there does come a point where you die. But this fall off is much more gradual than this fall off. And I'm interested in acclimation and how organisms respond evolutionarily to changes in their environment. And so there's a gecko that occurs in Africa and the Mediterranean region that was introduced into Texas that has then been expanding its range northward. So I look at a population in Galveston and a population in Edmond, Oklahoma, on the campus of the University of Central Oklahoma. And when we collect geckos, we measure their body temperature, we measure the wall temperature, and then we measure a bunch of random points on the wall. And these guys just crawl around on the walls all night. And so the only opportunity that they have for thermoregulating is absorbing heat from buildings. And so we put them in thermal gradients to see what their preferred temperature is. There are heat lamps at one end, and you can see little geckos interspersed in here. They move up and down these tracks to make themselves warmer by going close to the light or making themselves cooler going away from the light. And then we race them down racetracks. And these racetracks are run by lasers, and it outputs the data to a computer. And so we sit in a dark room at very cold temperatures and very warm temperatures and all temperatures in between, and we race geckos. So at times we will be working in the summer, racing geckos at cold temperatures. So we come to class, or we come to school in shorts and t-shirts, and then we throw on jeans and sweaters and walk into the cold room. And then in the wintertime, sometimes we come to school in jackets, and then we change into shorts and t-shirts and go into the room when we're racing things at hot temperatures. And so what we do is we collect a shitload of data. And so these are the kinds of data that we've seen. So this is winter and summer for the two populations, Galveston and Edmond, Oklahoma. And you can see that the environmental temperatures, the wall temperatures, and the body temperatures are all very different in the winter, and they're all very similar in the summer. This is what these regressions between wall temperature and body temperature look like. And so this is the kind of thing that I might be looking to see graphically from you as you look at these things. Or you could also do these in a set of isolated figures as well. It doesn't really matter to me how it comes to me. I'll be able to figure out. It would be nice, though, if you could standardize your y-axis so that I could compare across figures easily. But the easiest way to do this is to just use facets in ggplot to divide your data up this way. So keep in mind that the way you analyze your data might be separate from the way you display that data to make sense to someone. We race them, and these are the results of races. In some cases, they're running close to 1.5 meters, 1.25 meters per second, which is why we use lasers to time them rather than timing them with stopwatch. But then this is the body size and condition situation. And so you can look at these regressions and say, oh, that regression looks like it's different from that regression in the winter, but this regression and this regression don't really look that different in the summertime. And so one of the things that you might want to be able to do is to be able to compare the slope of this regression with the slope of that regression. Well, so it might be nice to know what the equation is for this regression and what the equation is for this regression and compare slopes. But of course, now I've given you a method for comparing slopes, at least for testing whether or not slopes are different. You could actually throw these into a two-way analysis of covariance, and you're not interested in what the body size is at some grand mean. You're actually going to use the two-way ANCOVA to actually look at the interaction term between the two, in this case, two variables, season and population, interacting with snout vent lengths. And then you use that interaction term to tell you whether or not these slopes are different. Once you have a slope that is different, and you know that there is a slope that is different in there somewhere, if there is a slope that is different, you can basically say, well, I think that this slope is different because the slope in winter is different from the slope in Edmond, Oklahoma is different from the slope of Galveston. You can actually use the slope of one to test whether or not that slope is different from the slope of the other. So you would run a regression on both of them, get the slope values. So you would have to partition the data up that way, get the slopes of both of those, then run the regression again on one of them and test it against the slope of the other one using that line of code that I gave you earlier on today. One of the reasons I gave you that line of code today is that, Grace, I didn't know you were going to ask this question, but I knew somebody was going to ask this question at some point. And so I might as well give everybody the answer all at once. Does that make sense?
I think so.
So go back to the regression example. If you have two regressions, you can run both of the regressions, get the summary output, and in the summary output, it's going to have the well, let's just do this. It's going to give you the value of the slope. So run, Oklahoma winter, run Galveston winter, get those two slopes, save them, write them down somewhere. Then run Galveston winter again, and then run this analysis on the Galveston winter model. And in this case, you would want, this would be SVL, because this is the snout vent length, snout vent length as it determines body size. And then you would put in here the slope from, the slope value from winter Oklahoma City. And that will then test whether or not Galveston winter slope is different from the slope of Oklahoma City winter.
Okay.
And just put whatever those. So this is the model that you used for analyzing the relationship between snout vent length and body mass. But then you want to test that against the slope that you observed for Galveston winter. And so you could actually test all of the slopes as being different from one another by just basically running two tests. Well, you would want more than two tests. You would want 4 tests, I guess, to test all the slopes against one another. But it's pretty apparent that this slope here is probably, these two slopes here are probably
Dr.
not
Klawinski.
different from one another. Yeah.
What would be our dependent variable and independent variable?
Well, so the y-axis is always the dependent variable. So weight is the dependent variable. SVL is the independent variable. So the syntax for this would be what? Somebody tell me.
Like LM, open parentheses, weight, and then the little
Hilda?
line.
Tilde.
Yeah, and then SVL, and then your data name.
Yep, that's the syntax. And you could do this once again on all of the data, or my advice would be to do this on subsetted data. So, one of the things that you guys said to me earlier on this semester is I want to get more practice using R. You guys on this assignment, you're going to use the hell out of R because you're going to be doing multiple episodes of simple linear regression on subsets of the data. So you're going to get practice subsetting data, you're going to get practice doing regression, and now you're going to get practice comparing regression lines to one another.
Okay, so my dependent variable comes first, and it is
The dependent variable always comes first.
dependent.
Dependent variable, this is basically asking, let me write this out. So one way of thinking about this is the the tilde means how does this thing affect this, where this is the independent variable. So this is what tilde means. How does this affect this?
Okay, and the report is asking me that the wall temperature, no, the body temperature
How does
influences
wall
the
temp,
size.
no. How does wall temp affect body temperature is one set of questions. The other set of questions is how does snout vent length affect weight? Because that's what body condition means. If you are 5'7" and you weigh 105 pounds, you're really, really thin. If you're 5'7" and you weigh 170 pounds, you're corpulent. You're on the
Yes.
hefty side. And so this regression here tells you that at a given body size, Galveston geckos are generally smaller in terms of weight than Oklahoma geckos are. And it's such a big difference that the whole reason that I looked at this is when you pick up a gecko off the wall, you can feel in your hand that those geckos in Oklahoma City are beefy. They're beefy and they're strong. You can't feel any of their bones. Some of the Galveston geckos are so thin you can like feel their backbone. And so
Wow.
something's happening in these two populations such that they're different sizes. And we're out of time. But if you have other questions, drop me a line and we can schedule a Zoom meeting or we can resolve things via email or whatever is best for you. Does that help, Grace?
Yes, it does.
Okay. All right. All right. You guys have a good weekend. Let me know if you have questions as you're working on this report.
Okay.
Yeah, sure thing.
You
Thank
too.
you.
See ya.